Hi, and welcome to this video in which we talk about the basics of counting. So, in this part, you have three different sections from the textbook 6.1, 2, and 3. Um, and each section corresponds to a part of this presentation. So, you will see with me today the first part about the basics of counting, the four basic rules of counting, and the Pigeonhole Principle. And later on, during the live session of the next week, um, which is our last session, we will see a couple of particular methods that are important in counting, which are permutations and combinations. So let's start with the basics of counting. So the principles are the product rule, the sum rule, the subtraction rule, and the division rule. You would see them with several other in the literature and under several other different names, um, and to master them, you need to work on um, a lot of examples actually to be able to identify the type of the problem and the method or the rule that fits it that may help you in solving it. We will also see how we can, in general, capture um, uh, the possibilities, the possible number of possibilities with the tree diagrams, which is a general um, let's say, framework or approach or method uh, to counting. So let's start with the first rule, the product rule. The rule says the following: if a procedure can be broken down into a sequence of two tasks, for the first one you have n different ways to achieve it, and you have n two different ways to achieve the second task, then uh, the procedure can be achieved in n1 times and two different ways. Let's see a couple of examples on this. So how many bit strings of length 7 are there? For every single example, please pause the video and think about it on your own and just compare after that. Don't be upset if the result is slightly different, um, um, but clearly you will start identifying how you approach these problems, how you think about them, and how they can uh, effectively be approached and solved. Okay, so you start identifying and adapting your way of thinking and to the patterns that you may find in the counting problems, and you will be able by the end of this video and the end of the next live session to create your own cheat sheet in which you have all the possible givens and possible um, problem aspects and how to solve them. So for this one, you should proceed maybe as follows. You would say it's a bit string to fill in a bit string of length 7. We need to fill in actually 7 different binary digits, okay, with either zeros or ones, okay. So so actually we have 7 different slots, and each one of them has 2 different possibilities, okay? Um, you can draw it as a binary tree, actually. You'd say, what about the first value? So you can either put in it 0 or 1, okay? We can also talk about 0 and the complement of 0, not 0, which is 1, okay? Well, if you choose 0, then you have 2 different choices for the second slot, which is also 0 or 1. But if you choose the first slot 1, then at the second place or slot, you also have 2 different possibilities, which are 0 or 1, and so on and so forth. So it's clearly a binary tree whose leaves actually would be equal to 2 to the power n, where n is equal to the number of levels that you have. So you can approach it in this way. You can also just say that you have 7 different slots, and each one of them has 2 different possibilities. So you have 2, 2 times 2 times 2, etc. 7 times, so which is 2 to the power 7. Good. So which is 128. Another example is how many AUB net accounts can be made for students if each account is composed of a sequence of 3 letters, case insensitive, followed by 3 digits. So all in all, so once again, the AUB net accounts they are composed of a sequence of 3 letters and then followed by 3 digits. Okay, so for the 3 letters, if it's case insensitive, so you just have 26 different possibilities, and for the digits you have 10 different possibilities. Okay, so each of them is picked up one or more times for the 3 places. So all in all, you have 6 different places, but you have for the first 3 places 26 different choices for each letter, and then you have for the other 3 places 10 choices for each letter. So all in all, it's 26 to the power 3 times 10 to the power 3, and this gives you all the possibilities. Another example that we have already tackled when we talked about the cardinality of the power set, we represented the subsets of sets as follows. So we said for each element Si inside the set, either that element exists or not. So either we have S0 or not S0. If S0 exists, so you can create another subset where S1 exists, or another subset where S1 does not exist. And both choices are valid when you have when you don't have S0 in the set. And you continue doing this for all the elements of the set, and at the end, actually, you would obtain so each path is in this tree, binary tree, is a possible, denotes a certain possible subset. So the number of possible paths corresponds to the number of leaves that you have at the end of your tree, which is once again 2 to the power the set of the size of the set. Okay. Good, and this is why we have 2 to the power the size of the set, different subsets. Let's consider a couple of examples about functions. So how many functions are there from a set with m elements to a set with n elements? So again, just draw it on your paper. So you have a set A whose size is equal to m, and then you have a a set B whose size is equal to n. So B is the codomain, it's of size n, and A is the domain, it has a size of m. So to think about the number of possible functions that you can create from A to B, we know that if, for a mapping f to be a function, it has to actually associate every single element of the m elements of A, of the domain, to one of the elements of the codomain. So you end up having possibilities for the first element. So we don't care if we have repetitions, we don't care if we are mapping this all the elements to the same element in B, or maybe some of them are mapped to other elements here and there, and maybe we have also the general case where some elements of B are not mapped to any element in A, they do not have any preimages. So in general, for it to be a function, the only one condition that you have is to map every element in A to exactly one single element from B. We don't care whether they are the same, they are different, there are certain elements left unmapped. So we care about the elements in A. So clearly we have m spots, okay? M elements, and for every one of them we have plenty of possibilities. We have n possibilities. So all in all, we have n to the power m different possibilities, okay? So what if we start imposing certain conditions on the function? For example, what if we want the function to be injective or one-to-one? Pause the video, think about it, and then when you're done, you will find out the following results. So actually, when you impose that every single image for any element in A is different than the other image of the other element in A. Okay, so for the function to be injective, every single element in A must be mapped to exactly one element in B, but that must be different than the images of the other elements. So again, since it's only injective, it's not necessarily surjective, so may have certain elements in B not mapped to any elements in A. But if you look at the possibilities where they are narrowed down right now, so for the first element, you have plenty of possibilities. Okay, so you have n different possibilities. But if you count the possibility for the second items, the second elements in A, you only have n minus one possibilities right now. Okay, so because you cannot choose the first element that has been already mapped to the first element in A. For the third element, you have less choices, so you're only left with n minus two choices, and so on and so forth until you have finally um, actually the last element, which is the nth element in A. Okay, so this is the first element in A. This is the second element in A. So for the nth element in A, uh, you would be left with n minus m minus 1 elements, okay, which is actually, you can also see it as n minus m plus 1 elements from B. And clearly this must be a positive number because you cannot build a function that is um, injective unless you guarantee that the size of B is greater than or equal to the size of A. Okay, so n clearly must be greater than or equal to m in this case. You will be able to accommodate all the elements of A um, with singular elements in B. Okay, and we will have a function for this somehow. So what if we continue doing this multiplication down? So after this element, so n minus 1 down to n minus m minus 1, okay? So which is, let's do it the other way around. So it's n minus m plus 1. So the next element naturally, okay, that is omitted from this multiplication is n minus um, m, and then n minus m minus 1 minus 2, etc. So down to 1, okay? So we know that this whole multiplication or product is equal to factorial of n, and we know actually um, that this one here, this part here that was omitted is equal to n minus m factorial, okay? So this is why this number here, the number of possibilities, can be denoted in short as factorial of n divided by factorial of n minus m. And we will see this in the live session part when we talk about permutations and combinations, particularly arrangements of permutations. Okay, so you can see the details in the slides later on. One last example about the product rule is the size of the Cartesian product of multiple sets. So we have already discussed this earlier, and we showed you that the size of the Cartesian product is equal to the product of the size of all the elementary sets that are implied in the Cartesian product. What about the sum rule? So if a certain procedure can be carried out by choosing only one out of two different tasks, then if task one can be solved in n different ways, and task two can be solved in n different ways, and two different ways, where none of them are similar, okay? None of them are similar. Then there are exactly n1 plus n2 different ways to do the original task. Example, you want to a mathematics department must choose either a student or a faculty member as a representative for a university committee. The department has 37 different faculty members and 83 different students. So how many choices are there for this representative? So actually, um, you only have 37 choices plus 83 different choices. Okay, so you are left with 120 possible ways to pick up a representative. Okay, because you can either pick up one of those faculty members or one of those 83 students, and there are no redundancies between them. Okay, so none of these 37 and 83 possibilities is redundant or similar. So it's quite, it reflects quite a bit the rule of the size of the union of two sets where the sets are actually disjoint. Okay, so when the sets are not disjoint, um, we have certain repetitions, and this is why we should subtract those redundant cases. And this leads us to the subtraction rule that we will see in a few minutes. So in general, the size of the union is equal to the sum of the sizes of the sets, as long as we guarantee that they are pairwise disjoint. And in the case where we have common elements, we have to use the subtraction rule. One example on the summation rule, suppose values in a programming language can be either a single letter or a letter followed by a digit. Okay, so find the number of possible variables. So if like actually these two possibilities have nothing in common, for this one, we know that the number of possibilities is 26. And for that variable name pattern, we have actually 26 times 10 for the 10 different digits. Okay, so A0, A1, okay, and then B1, B0, B1, and so on and so forth. So all in all, actually, you would have the summation of these two possible cases, which is 286. Let's count those passwords. Suppose you have a password system on a certain computer where the password is 6 to 8 characters long, and where each character is an uppercase letter or a digit. How many possible passwords are there? So if you look at the problem, you notice that you can cut it into 3 subproblems. So if I ask you to count the possible passwords of length 6, okay, that have this property, they are uppercase letters or the digit. So it means that you have 26 plus 10 possibilities for each character. So it means 36 or no. So you know that you have 36 to the power 6 um, um, different possibilities. But this is only for passwords of size 6 characters. Okay, but your passwords might also be of size 7, okay, or of size 8. And the passwords of length 7, they have nothing to do in common with passwords of length 6. They are completely different. They have a fixed length of 7. Okay, so if all in all the password of this machine can have a length of 6 up to 8, okay, then we should count the passwords of length 6, 7, and 8, and then we can sum them up to find the final total number of passwords. Okay, I already explained here the case of passwords of length 6, and you have the details in the slides because the others are quite similar. You just have to do the math and then you sum them up and you get this very large number. So you can use Excel or a calculator to do this calculation. So what about the subtraction rule? It goes hand in hand with the addition rule. or the sum rule, and actually it happens when you have certain redundancy between the ways of among the ways that you have actually counted. So it's also known as the inclusion-exclusion principle. So when you are calculating the size of A union B and you start with the by summing up the size of A and B, then you have also to exclude or to subtract the size of the intersection of A and B, because you would have counted it twice. Okay, the elements in the intersection would have been counted twice, once inside A and once inside B. So we have to exclude them once to compensate. For example, how many bit strings of length 8 either start with, so once again, we have an or here, okay, so it's kind of a union. So either start with a 1 bit or end with two 00 bits. Okay, so it's either start with 1 or and with 00. So I think the first one is quite easy to calculate. So just it's 2 to the power um, um, 8 minus 1, okay, because 1 bit has been fixed to 1. And this one is quite easy also because it's 2 to the power 8 minus 2, because we fixed 2 bits and we only left with 6 different bits. So it's 2 to the power 6. But we cannot simply sum up those two numbers, okay? Try to think about it. Why? Are there any intersections between those strings here and there? Okay, so don't you think that there are plenty of those bit strings that end also with 00, and they would have been also counted here? Or vice versa, plenty of those that ends with the 00, they also start with 1, and you counted them inside these possibilities. So maybe you also have to subtract from them the possibilities where the bit string starts with 1 and end with 00 at the same time, because this is the intersection of these two sets, okay? And which is 2 to the power 5. So all in all, you will find this result, and the details of the calculations are given in the slides. We can reconsider the same 6 to 8 characters long password problem, where each character is an uppercase or a digit, okay? So something that we just done a few slides ago. But we can add to it this constraint, so where each password must contain at least one digit. Well, when you have the at most and the at least, X digit or X character or X choices, well, you have to approach it maybe in its complement form, because when we say, let's focus on the P6, which are the set of passwords of length. Okay, P of length, um, where the length of P is equal to 6, okay, etc., etc. And the password P fulfills the conditions given above. Well, inside those passwords, um, you have actually to exclude the case where you don't have any digit at all, okay? So you can approach this problem in two different ways. Either you count the case where you have exactly one digit, or exactly two, or exactly three, or exactly 4 digits, or exactly 5 digits out of 6, or exactly 6 digits, okay? And then you do a certain union, okay? But it's really a burden, okay? Or you can consider the complement of this. So you count all the possible passwords, whether they include digits or not, and then you exclude the complement, which is no digit. Okay, so you exclude the passwords of length 6, where you have actually 0 digits in them. Okay. I think you would prefer this one. Okay, you should be able to do this one too, but yeah, it's just much harder. So and when you have at most, you can also reason in the same way. So it depends on the at least or the on at most uh, um, um, case that you have. So for example, if I say at least 6 digits, well, it means it's exactly 6 digits. Okay. So in this case, I won't go for the exclusion here. Okay. I won't go for the complement. If they say at most one, it means only, so it's either with 0 digits or with 1 digit. So it's easier for me to handle right away. But sometimes when you have such cases, it's much easier to consider the complement. So just consider this possibility. And you should do the same for actually for the P7 and the P8 that we calculated a few slides ago, just to exclude those cases where you have 0 digits. So if we try to think about the passwords where we have okay, 6 different characters that are letters or digits. So we saw that it's equal to 36 to the power 6. And what about the passwords of length 6 that have no digits in them? Well, they are constituted mainly out of letters, 26 possible letters. So for each character here, we would have chosen 26, one character or one letter out of 26. So we'll end up having 26 to the power 6. Okay. So we should exclude this number from that number to get the exact number of password that must contain at least 1 digit. You have again the details and the exact numbers in the slides, so you can refer to them. What about the division rule? So we still have the division rule and the general approach of tree diagram. And then finally, the pigeonhole. The division rule, if a procedure can be done in n ways, and for each way w, exactly the other ways of out of the total of n ways correspond to the way w, then the procedure can be done in n over d distinct ways. Okay, so it's quite natural, but sometimes when you read it, you keep on reading it again and again, and you find yourself lost if you don't take certain examples. So let's see certain nice examples about this. So for example, imagine a set A that is made out of union of n different pairwise disjoint subsets. Okay, so practically you have n different subsets. So A1, A2, okay, A3 up to AN. And the size of the AIs, okay, is equal to D. So you have D elements in each set. So this is what reflects that when you pick up a certain way W, any W actually, you see that the other elements are similar to it. Okay, so this is what is leading us to group all these W's inside the same A. So if the total number of ways is the set A, okay, and if you are interested in representatives of these possibilities, well, finally, it means that the total number uh, of elements actually or ways, different ways, is equal to n divided by d. Okay, so here, for example, the size of A, if we divide the size of A by d, we get n. Okay, so because we have n different sets, finally, that are disjoint, that represent different possibilities or different solutions. Let's consider another example actually that concern functions. So it's also useful to see it for functions in this way. Imagine that you have a function f that maps every d elements, okay, every d elements of A to one single element of B. So maybe those D elements to Y1, those D elements to Y2, and so on and so forth. So all in all, you would find that the size of B is equal to that number n, okay? And the size of A would be equal to n times D, okay? Um, or simply that the size of B is equal to the size of A over D, because we have grouped the possible all the possible redundant ways in A into non-redundant disjoint sets of D elements each. Okay, so we are cutting the total number of possibilities in A by D to get the total number of non-redundant ways, which is finally n. Example on this: how many ways are there to seat 4 people around a circular table, where 2 seating plans are considered the same when each person has the same left and right neighbor? So let's explain this. Okay, what do we mean by 2 equivalent seating plans? So just for example, all these 4 different seating plans are equivalent according to what we learned on the previous page. Um, in the seating plan, P1's left is P2, and P1's right is P4. Okay, so necessarily P3 is facing P1. And if you look at this seating plan, you'd find the same thing. So P4 to the right and P2 to the left. So hence P3 is facing P1. It's the same thing again and again. Okay. So as long as we don't care whether, um, so suppose that on this table, we don't care about the one sitting near to the window, or the one that's sitting to the left of us, the readers of this schema. So just a circular table, and it does not really matter uh, um, um, where they are looking, or what they are facing, other than each other. Then all these seatings are the same. It's really the seating where P1 is facing P3 and P4 is to the right of him and P2 is to the left of him. Okay, it's really the same seating. So all these 4 different possibilities, they are the same. So this is why, to solve this problem, you have to think about all the possible seatings, and then you have to divide by 4. Okay, so the number of seats around the table from 1 to 4, proceeding clockwise. There are 4 ways to select the person for the seat number 1, 3 for the seat number 2, 2 for the seat number 3, and just 1 way for the seat number 4, which is finally factorial of 4. Okay, it's 4 times 3 times 2 times 1. Nevertheless, these possibilities are not all to be counted. Every 4 out of them are the same. Okay, so this is why we have to divide by 4. Okay, to finally find the 6 different seating arrangements that we have. And once again, this remark will pop up again when we talk during the live sessions about permutations and arrangements. Okay. So in general, we can solve many counting problems through the use of a more general approach, which is the tree diagram, um, in which a branch represents a possible choice and the leaves represent all the possible outcomes. I already did this exercise with you when I counted using a binary tree, the bit strings um, um, on the possibility for the bit strings or for the power set. But we can also consider actually irregular cases, actually, where we don't have regularity, we don't have a binary tree, we don't have a tree with a fixed number of branches each time. So suppose that I love discrete math, t-shirts come in 5 different sizes: small, medium, etc. So each size comes in 4 colors: white, red, etc., except XL, which comes only in red and in green and in black, and XXL, which comes only in green and black. Okay. So once you start having those irregularities, then you have, maybe it's better to count carefully the possibilities. Okay, and the tree diagrams come handy in this case. So to draw the tree diagram, so first of all, we can count the possibilities for the size, which are 5 different sizes. We know that those subtrees are complete. They have all the four different choices, white, red, green, and black. But we know that, so maybe we can do the usual multiplication rule here or product rule, and then we know that we will end up with 12 different choices. But then with the union or addition rule, we can add those particular special cases where we only have three possibilities for the XL and two possibilities for the XXL. So clearly drawing the diagram will help you, but also you can do it by hand on paper without the diagram, just in case it's faster and clear for you. Um, Another example that shows you the importance of using this method is where you have two teams, and they are competing for the first and second places by playing successive matches. And the team that wins the three matches would win the final tournament. So, in how many ways can the tournament be played? Well, you have plenty of different irregular choices, and it's really important to build a tree to count the possibilities. So your tree would be symmetric, actually. It's kind of a mirrored tree because if in the first match T1 wins, uh, you would have all these possibilities. But if 2-2 wins, then you may also have all the subsequent possibilities. So if T1 wins, then maybe the next match T1 wins, and then T1 wins, and then it's over. Okay. But if T1 wins, if after T1 wins, T2 wins, well, here you may have two different possibilities. Either you will have two successive wins for T1, or, okay, and I think you saw what's happening. The same after two wins for T1, maybe you have one win for T2, and then again T1 would make it, or two wins for T2, and then maybe T1 would make it, or finally maybe T2 would make it. Okay, so you can see that we have here all the possibilities, and when you count the number of leaves, you'd have the total number of possibilities, and as you saw, sometimes you don't need to draw all the tree because you have redundant cases, you just multiply by two at the end. Yeah, so all in all, you will see that you have 20 different possibilities, quite a regular pattern here, and maybe the rules that we introduced to you earlier, the four rules won't be helpful unless you draw the diagram. And now we get to a final topic here, which is the pigeonhole principle. Okay. Well, actually, it's divided into two part. The first one is the basic pigeonhole principle, and then another chunk which is about the generalized pigeonhole principle. So let's see the motivation for this. Suppose a flock of 20 pigeons fly into a set of 19 pigeonholes to roost. Since there are more pigeons than pigeonholes, then there must be at least one pigeonhole that has more than one pigeon in it. Try to think about it. Replace pigeons by books, and replace the pigeonholes by, let's say, bookmarks. Okay, and then if you don't have enough bookmarks, then at least one book would be left without a bookmark. Okay, so it's quite intuitive. Nevertheless, we're going to prove it. So what we want you to think about it all the time is that this is the least. Okay, so maybe in some of your books you are using more than one bookmark because there are two different chapters that are really important in one of the books. So you really need two different bookmarks for the same book. Okay, so in this case you will be using two for one book, and then 17 for 17 other books. Okay, all in all you will be just covering 18 different books, and you will be left with two different books without any bookmarks. Okay, so do you see? And the case where we have this is this case here. So we did our best to put one pigeon in one hole, but we will absolutely be left with one pigeon without a hole, or actually one of the pigeonholes with two pigeons in that. Okay. Um, if we leave the decision for them, so maybe they will choose a completely random different way. Maybe all of them they will be sitting within the same um, um, pigeonhole. So maybe you would use all the 19 bookmarks for only one book, and you will leave all of the other books without any bookmarks. So it's really up to you. But what we would guarantee is that at least one book would be left without any bookmark. At least one hole would have two different pigeonholes in them. Okay, so you should be able to imagine this, to think about it, to write it on paper, to explain it to yourself. But you also have a nice proof here. It's a proof by contra position. While we suppose that none of the K boxes has more than one object, so simply the total number of objects that you can put into K boxes is at most K. So by contrapositive, you can imply that when you actually have K plus one, at least one of them would have one object in them. Okay. A corollary of this, we can prove that a function f from a set with K plus one elements to a set with K elements is not and cannot be one to one. Okay, so do you see it? So if you have K plus one elements here, and you have K elements there, no way you can make it a function and injective at the same time. Okay, so because you have more elements, and every single element, for it to be a function, every single element must be busy with another element from here. Okay, so if there are more elements in A, then clearly at least one of the elements in B has two different pre-images. Okay, so you cannot make it injective, impossible. Okay, so maybe all of them actually are pointing towards the same element in B, except this one. Okay, so this is still a function. Okay, but it's not a one-to-one. Okay, what we want you to think about is that when you try to make it one-to-one, you will see that we will fail at the end. Actually, we cannot make it because we have more elements in A. We have already discussed this when we talked about functions and injective functions, but we can also prove it using the pigeonhole principles by considering the elements um, actually in the codomain to be the boxes or the pigeonholes, and the elements in A to be the pigeons. Okay. Let's consider this example. What is the least number of people who shall be in class to guarantee that at least two have the same birthday? Okay, the same birthday. At least two would have the same birthday. How many students? Just recall that, or let's assume that we have 365 different days. Okay, throughout the whole year. Okay. So how many students there should be? Let's see it. Yeah, so actually, suppose it's 366 different days, then you need 367. Okay. If you consider it's 365, then you need 366 different person. Okay, because there are 366 possible birthdays. Okay, so you can consider those birthdays all the day of the year. Okay, as boxes. Okay, and you have people in to accommodate in them. Okay, so maybe all of if you have 366 or 67 different person in a class, so maybe all of them they were born on the 1st of January. Okay, so on one single day. Okay, but this does not contradict what we said. At least two have the same birthday. What you just showed us that all of them were born during the same day. Okay, but there is a guarantee that at least two would be necessarily born on the same day, because even if you try to accommodate all of them in different days, so finally we'll be left with one additional person who has to be born somewhere during the year, like someone else. Okay. Um, what about the generalized pigeonhole principle? Well, actually, if you have n objects and you want to place them into k boxes, where typically n is greater than k, then there is at least one box containing at least, so there is at least one box containing at least the ceiling of n over k object. Okay, so we have these two guarantees, at least one of the boxes and at least the ceiling of n over k. Let's see. A proof by contraposition. So suppose that none of the boxes contain more than the ceiling minus one, ceiling of n over k minus one objects. Then the total number of objects would be equal to this multiplied by that number, okay? Because we have k boxes, okay? And this is the maximum, okay? It can be at most this. Now the question, can you compose n different objects out of this? Well, actually you cannot, because we know that the ceiling of n over k is strictly less than n over k plus 1, and therefore, if you actually do a little bit of math, so if you subtract 1 from each part and then you multiply by k, here you get n on one hand, okay? But on the other side, you get this actually, which is actually this total number of boxes. So this is greater than or equal to the total number of objects that you can accommodate on k boxes. Okay, and this is clearly less than n in this case. So, which means that there must be in at least one of the boxes at least the ceiling of n over k, okay, and not less than that. Just to know how to use the um, generalized pigeonhole principle and the pigeonhole principle. So let's apply it on those couple of examples. Among 100 people, how many were born in the same month? So again, here we're considering the month, and we have 100 different person. Okay, so think about it, and yeah, even if you try to distribute evenly those persons over the 12 months, okay? So you would add 12 person, one in each month. And then by the way, starting from the 13th person, you will start to have repetition. And this is already given from the basic pigeonhole principle, okay? Even if you try to distribute them evenly again, you will have at least two different, in at least one of the boxes, at least two different persons starting from the 13th, etc., etc. And then you can generalize this up to the 100 over 12, because ceiling of the 100 over 12, which is equal to 9. Okay, so clearly at least one of the month, okay, we don't know which one, but at least one of them would have at least 9 different person. Okay, you cannot have less than that for all the month. Okay, necessarily 9 at least in one of the month. Okay, so maybe 9 are there, and the 91 or in other month. Okay, but it's fine. Or maybe nine, like maybe you put 99 in one of the boxes and then you put one in another box, and then you show me that there are plenty of boxes or plenty of months where you don't have anyone born in them. But I would say, yeah, so the box that contain 100 or the 99 or whatever number you want has already at least 9 in it. Okay, so the only way to contradict this is to try to distribute them evenly, as I started explaining, and this would end up having 9 at least in each, in at least one of the boxes. Not in each, but in at least one of the boxes. Okay, Let's consider this example. A ball contains 10 red balls and 10 yellow balls. How many balls must be selected to ensure 3 balls of the same color? So at first, maybe you will think about the special case where yeah, you're designating a certain specific color in your hat. So what about the possibilities? How to guarantee that 3 red balls are selected or 3 yellow are selected? So if you fix the color, I agree with you that you would need actually 10 plus 3 from the other stack, okay? So to guarantee that you will get finally 10 yellow out of what you select from the total number of balls, well, you need 13 at least, okay? Because maybe 10 out of the 13 are red, but since you have 13 in hand, then necessarily the 3 others would be yellow, okay? Or vice versa. But here we are asking about something different. How many balls must be selected to ensure 3 balls are of the same color? We don't care which color uh, is it, okay? And if play the game, so maybe you want to show me, so what is the minimum number of balls that you need to select? So maybe you want to make it harder for me to find 3 balls of the same color. So we'll start altering those colors. Okay, so you select 1 red and then 1 yellow. Okay, and then you torture me, and then you select 1. You say that it's a red one. Okay, but even if you want to delay to the max, the selection of 3 balls of the same color, you cannot let me wait more than this. Okay, so after 5 balls maximum. Okay, so at this moment, one of them will be of the same color of 2 of the other 4. Okay, and maybe earlier, so maybe by coincidence, I would have selected the 3 that are yellow, or maybe the first red, or maybe 1 red and then 3 yellows. Okay, so maybe at 4, but at least after 5 attempts, I will absolutely find 3 balls of the same color. And this is due to the generalized pigeonhole principle. So as if we had 2 boxes, okay, as if each color is a box, and then throwing those 20 balls in the boxes would guarantee that at least one of the boxes would have um, 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 this actually required number so the question is how many balls you should select to have them to have a 3 in the same box. So we should find the minimum number n such that the ceiling of n over 2 is equal to 3. Okay, so where n is the number of balls to pick. And if you do the math, you'd see that in this case, n would be equal to 3 minus 1 multiplied by 2 plus 1, which is 5. Okay. And again, yeah, this is different than selecting 3 balls of the same color, which requires selecting in the worst case, selecting the 10 wrong balls and then selecting 3 of that color, which is 13. How many cards must be selected from a standard deck of 52 cards to guarantee that at least 3 cards of the same suit are chosen? Well, again, it's you want a minimum number n such that um, the ceiling of n over 4, because you have 4 different suits, is greater than or equal to 3. Okay. Okay, so we want to guarantee that 3 cards actually are the same suits. It's the same concept, and the smallest integer is 9 in this case. Okay, this is different than how many cards must be selected to guarantee that at least 3 hearts are selected. Okay, if you specify the suit, then clearly you need to select. You need to count the worst case where 39 cards have been selected from the three other suits, and then if you want a three from the hearts, you still need three additional cards, so you need to select up to 41 cards to find three hearts. You can also consider this example on your own. You have the answer key in the slides. I don't want to be that long on you. And a couple of other examples. So one about the triangles and about the midpoints of integers. They are very well explained. And next time during the live, we will be talking about the last part after having your questions on what have seen so far. And those parts are permutations and combinations. Thank you for listening, and see you